Okay, welcome to a lecture on stereochemistry and chiral molecules. In your book, in the Deniston text, this is covered in the chapter on carbohydrates. It's chapter 16. This is from a different textbook. It was covered in chapter 15, but that's fine. This is, for us, this is chapter 16. And I remember when I first was introduced to stereochemistry and this thing called chirality. Here they talk about chirality. I found it very difficult, so I'll use this lecture to try to make things a little bit easier to understand. So first off, let's just review isomers a little bit. If you recall, isomers are compounds that have the same chemical formula, which means they have the same number and types of atoms, but these atoms are arranged differently. And there's two main types. There's constitutional isomers and stereoisomers. This chapter 16 is talking about stereoisomers. Constitutional isomers we've already talked about, and I'll give you a quick example. We could have this compound that would be 2-propanol or isopropanol. It's an isomer of N-propanol. So you notice we have 1-propanol or 2-propanol. They have the same number and types of atoms. They have the same chemical formula. It would be C3H8O. I left off all the hydrogens for simplicity's sake, but these two compounds are constitutional isomers. And then we have stereoisomers, and we've actually already introduced to stereoisomers in that geometric isomers are a type of stereoisomer. So you've seen cis-trans isomers in a couple different places. First off with alkenes, right? We could have this compound, because you lose that rotational freedom around a carbon-carbon double bond, you could have cis-2-butene. And we'll put down here trans-2-butene. So the hydrogens are on opposite sides, or if you wish, you can think of the methyl groups here are on the same side, so that makes it cis, and this guy is trans. They're on opposite sides, it's trans 2-butene. And these compounds, although they have the same number and types of atoms, are going to have different chemical and physical properties because the atoms are arranged differently. All right. Where you also saw geometric isomers was with cyclic compounds. So we'll draw a cyclohexane ring here with this edge here coming out at us. And we could put a methyl group on one side and a methyl group on the other. So this is two methyl groups are on opposite sides. So this is trans 1,3-dimethylcyclohexane. I'm not going to write the whole name out because what's most important for us is to recognize that this is trans. These two guys, these two methyl groups are on opposite sides. And I could draw the cis where they're on the same side, where they're see how they're both on the top or both on the bottom. And again, when you make a carbon-carbon double bond like this, you lose that rotational freedom, which generates this cis-trans isomer. Likewise, when you make a ring structure, you also lose rotational freedom, and these methyl groups are stuck on either the same side, which would be cis, or in this case, the opposite sides is trans. Then we get to these things called stereoisomers. I'm sorry, not stereoisomers, enantiomers and diastereomers, also a class of stereoisomers. So stereoisomers also include these cis-trans or geometric isomers. But what are these enantiomers and diastereomers? Well, first off, enantiomers and diastereomers requires the presence of a chiral carbon. Okay, well, what does that mean? So I'll just say here requires a chiral, this is pronounced chiral, CH, but it's chiral carbon. And then there's two main types, enantiomers, which happen to be mirror images of one another. And one of the things I struggled with was trying to find a YouTube video where some other instructor or teacher, professor talked about enantiomers. And the thing that they always forget to mention is that everything has a mirror image. These diastereomers, they have a mirror image as well. If you put one in front of a mirror, it would have a reflection. That's not what's special. What's special about these enantiomers is that the compound and its mirror image are not the same. So the mirror images are isomers. They're not the same compound. So they're mirror image isomers. Not the same, and we'll show you some examples of what we mean by that. Diastereomers, if you have two compounds and we say, okay, these are diastereomers of each other, they are not mirror images, but they do have a mirror image, and that mirror image would be its enantiomer. So that gets a little confusing. Easy way to keep enantiomers and diastereomers kind of separate is that diastereomers requires actually 2 or more chiral carbons. You can have an enantiomer or a pair of enantiomers, a compound in its mirror image, with only 1 chiral carbon, but diastereomers must have 2 or more chiral carbons. So chiral or achiral. Chiral comes from the Greek word for hand. Your hands are a mirror image. Your left hand is a mirror image of your right hand. If you put your right hand up to a mirror, your left hand is reflected back, and vice versa. They're often referred to as asymmetric or also non-superimposable. So they're non-superimposable mirror images. So you can do this, and I have a little video, I think, showing you this concept in a little bit. But if you take your right hand and left hand, you can place them one on top of the other, and you can get the thumb and the fingers to line up, but you can't get the palms to line up. They'll be, one will be palm down, one will be palm up. So you could fix that, but by flipping one hand over, but then of course your thumbs and your fingers will be on opposite sides. So they're non-superimposable mirror image. It means they're chiral. It means that this, say if the left hand is the object and this is its mirror image, they're two different things. Down here, these socks, provided it doesn't say left and right on them or something, these would be achiral or not chiral. This sock has a mirror image, and you can place one on top of the other, and there's no way to tell one from the other. They are superimposable. So these are not, in this lesson, these would be not chiral. So they're not isomers of each other. They are the same. So if you have two compounds where all the atoms line up, they're not isomers of one another. They're actually two copies of the same compound or the same molecule. All right, so now let's look at some compounds. Water is achiral. Water on the left and the water on the right. These two hydrogens are reflected back, and then the oxygen in the middle, and the hydrogen furthest from the mirror is reflected here, furthest from the mirror. And you could take one molecule out of the mirror and stick it onto the other one, and all the atoms line up, so they're superimposable. They are superimposable, so they are not chiral. This compound, bromochloromethane, is likewise achiral. Here we have the, this would be the chloro, green guy, here's the bromo. Chloro is reflected to the chloro, the bromo to the bromo, carbon in the middle, hydrogen on top. And you could pluck this guy out and rotate it 180 degrees. And actually, let me go ahead and list this guy as hydrogen number 1. This is hydrogen number 2. And if we rotated it, what you'd find is we could have this hydrogen number 1 still on the top, but then this chloro would be coming out towards us. Well, that's okay. What we would do is just flip the molecule around so that this is now hydrogen number 1 and this is hydrogen number 2, but you know what? One hydrogen and another hydrogen are identical. You can't tell them apart. Now, I happen to label them 1 and 2, so now we can, but in practice you can't. And so all the molecules actually line up, and this is likewise achiral. Now we get to bromochloromethane. We have a carbon in the center and 4 different things, right? We've got the chloro, the bromo, fluorine is the smallest of the halogens, and then hydrogen. It's got 4 things attached, and it turns out it doesn't matter which way you pluck this guy out and rotate about, you'll never be able to get all of these guys to align. Okay? We have the hydrogen lined up, the fluorines lined up, but the chloro and the bromos are not. And there's no way to translate or rotate this object to get it to line up with this mirror image. So they're non-superimposable mirror images. They are enantiomers. So non-superimposable mirror images non-superimposable mirror image isomers. These are referred to as enantiomers. Big deal. They're pretty much the same thing. I mean, is that really going to make that big of a difference? Well, you'd be surprised. And then you'll see when we get into carbohydrates why this is such a big deal. Okay. So enantiomers are mirror image isomers that are non-superimposable. We pronounce this chiral. Oh, and the other thing I forgot to mention, in order for a carbon to be chiral, we talk about this chiral carbon, it must have 4 different atoms or groups of atoms attached to it. So we had the bromo, chloro, fluoro, and I don't think we had iota, we had hydrogen. But let's go back here a second, right? So bromo, chloro, fluoro, and hydrogen. If there's 4 different atoms or groups of atoms attached to a carbon, then it is said to be chiral, and it's will have a non-superimposable mirror image, which we call an enantiomer. All right. So this carbon is likewise chiral because it has a hydrogen, a bromo. Those are clearly different. And then we have a carbon and a carbon. Well, aren't those 2 carbons the same? Well, not exactly, because you see, it's not just the one atom that's attached to, it's everything on this side. So we have 3 carbons here and 2 carbons here. And so the right-hand side is different from the left-hand side. And so this is chiral. So it's a bit like when you alphabetize. If alphabetizing names and the 2 people start off having the same first letter, fine, you look at the next letter. So these guys are both carbons, a CH2 and a CH2. Those are exactly the same. You go to the next one, a CH2 and a CH3. And so clearly here, this guy is different from this guy. And so there's 4 different, what we call moieties, or if you wish, just atoms or groups of atoms attached to the carbon, and that makes it chiral. Or you also hear these terms: asymmetric carbon, a stereogenic center, or a chiral center. There are some other atoms, just a few other atoms that exhibit this property of chirality, but it's pretty uncommon, and we'll just stick with carbon. So where are the chiral centers in these guys? If you want, you can pause it and take a look, study these real quick, and see how they are arranged and figure out which ones are chiral. Remember, you must have 4 different atoms or groups of atoms attached. Okay, so this carbon at the top of penicillamine has only 3 atoms attached: an oxygen in this carbonyl and an oxygen in this hydroxyl, and clearly these are different because one's an O, one's an OH, and then the rest of the molecule. So you can think, well, there's only 3 atoms attached, so it can't be chiral, it must have 4. Or if you wish, you could say it's attached twice to this oxygen, and you know what? This oxygen is exactly the same as this oxygen. So again, only 3 different things attached, and it's attached twice to this oxygen. These carbons down here, clearly not chiral. They have 3 hydrogens attached. Those are indistinguishable. This carbon here, well, we've got the rest of the molecule going up, a thiol at the bottom, and then we have a carbon and a carbon. Well, those are exactly the same. This methyl group is indistinguishable from this methyl group. So again, this is not chiral, but this guy here is. I'll put a little star here. Right? We've got the acid group on the top, the carboxyl group on the top. We have the amine on the left. We have a hydrogen and the rest of the molecule. So there are 4 different things here, and this is a stereogenic center, or the chiral carbon. For albuterol, albuterol is a drug used for asthmatics, bronchodilator. Albuterol has a chiral carbon as well. None of these carbons in this benzene ring that have a double bond are going to be chiral, because you must have 4 things, and if you wish, I'll put a hydrogen. They don't show the hydrogens, but these are carbons. And if a carbon only has 3 things attached, it cannot be chiral. This guy's in chiral, has 2 hydrogens. This guy here is the chiral carbon. Maybe you notice that right away. Right? It has an alcohol, a hydrogen, this amine chain here. The amine is a nitrogen, and then the benzene ring. So the left and the right are clearly different, top and bottom different. So this is chiral. Now, one of the things that these videos I was looking at online often don't talk about is this idea of optical activity, and I think it's an important thing to consider, because the neat thing about enantiomers is that it's a subtle difference between the one compound and its mirror image, but they are different, and the only physical difference that they exhibit, they're going to have the same boiling point, same melting point, same viscosity, same density. Every physical property you can imagine is the same, except for this thing called optical activity. Okay, so what is optical activity? Well, you might be familiar with the fact that light travels in waves. Sometimes people talk about light as a particle or as a wave, but in this case we're going to view light as a wave. So say this is the direction you turn a flashlight on, and this is the direction that the beam is going, and we can just draw a sine wave here. It goes up and down. When I say sine wave, if you had it in trigonometry, don't worry about it, but it's a sine function. Okay, so it just goes up and down, kind of like, you know, the waves in Lake Michigan or your bathtub or something like that, right? And they travel down here. And the thing about light waves, though, if it's unpolarized, the light waves are always perpendicular to the direction of propagation. So let me put another wave in here that is also perpendicular to the direction of propagation. And so this is coming out at you and going into the screen, coming out and going away from you. So we have one going up and down, one going in and out, and it turns out that all waves, because this is the direction of propagation is one dimension, every single angle here is likewise, if I put this is the direction of propagation of the light, every angle is going to be 90 degrees to that direction of propagation. So you've got light going up and down this way, in and out like I drew here in red, up and down as I did here in blue, and then on this any angle 360 degrees around would be perpendicular, and that's what we call unpolarized light. And then you can send it through what we call a polarizing filter. Sometimes people will call these a polarizing lens, but it's actually a filter. Lenses are designed to focus light. This does not focus the light. This simply filters the light. And if you have a pair of polarizing sunglasses, actually you'd need two pairs of polarizing sunglasses. These have a polarizing filter on them, and I won't get into how that works or whatnot. But basically what happens is the light that goes through, it's kind of like a picket fence, and so only the light that's vibrating vertical can get through. The light that's going in and out is going to rattle in this the pickets of the fence and stop, but the light that's going up and down can pass through. Now if you had two pairs of polarizing filters or two pairs of polarized sunglasses, you could put one up and down and put the other pair perpendicular, and it would block out all the light. So I invite you to go to Walgreens or Target sometime and pull a couple of polarized sunglasses off the rack there and put them 90 degrees to one another, and you can see what I'm talking about. Alright, so this is now polarized light. It's only vibrating in one plane. It's plane. So when they say plane polarized, they don't mean airplane. They mean it's only vibrates in one plane. Just up and down. Okay, ordinary unpolarized light vibrates or oscillates in all planes. Okay, so what's this got to do with stereochemistry and these chirality and all this stuff? Well, if you take a chiral compound and you put it in a sample tube, say, or if it's a solid, you could dissolve it in water or something like that. If it's a liquid, you just put it in the sample tube and shine this polarized light through it. What will happen is it will rotate this plane of polarized light, and so there'll be another filter here. Now initially these two had to be lined up, so this one is stationary, doesn't move, but this one you can rotate, and it would be vertical so the light would shine through. But what you have to do to get this to the light to come through is you have to rotate this down a few degrees so that the light that's rotated by your chiral compound can now come through. All right, so that's optical activity. And compounds that are chiral are said to be optically active, and they have this what they call this alpha here is the degree of rotation. Okay, and this is the only property that's different between chiral compounds, or I should say between enantiomers. So there's something called specific rotation and absolute configuration. A lot of the videos again go into something called absolute configuration, or R and S configuration. Your book doesn't talk about it, and I'm not going to talk about it, but if you look online, you'll see people discussing R and S assignments, and I'm not going to get into that. Well, all I want you to recognize is these two compounds are mirror images. We could put a mirror plane through here. Right? This hydrogen is reflected to this hydrogen, this alcohol group to here, likewise. So this is glyceraldehyde, this is glyceraldehyde. Okay. One has a specific rotation of minus 8.7 degrees. The other has a specific rotation of plus 8.7. So the degree of rotation is exactly the same, but the direction is opposite. Well, why is that? Because they're mirror images, right? These are enantiomers. Okay, so one's plus and one's minus. If it rotates light to the left, and what that means is in that polarimeter, that we saw on the previous slide, we would have to rotate this guy to the left 8.7 counterclockwise, and we refer to that as levorotatory. So levorotatory, let me use red here. Levorotatory means it has a minus specific rotation. Dextrorotatory means it has a plus specific rotation. Okay? And that's the only physical property that's different between these two. Now there might be different chemical properties, but in terms of physical properties, boiling point, melting point, solubility, density, refractive index, anything else, physical properties, they would all be the same except for the specific rotation. They're equal degree but in opposite direction. This one would be going, let me draw my polarimeter here. You would have to rotate this guy to the right. So it's plus 8.7 degrees. Okay, I'm going to take a little break here and show you another video that shows these molecules in a little bit closer, better detail, and how one is a mirror image of the other. And then we'll start talking about Louis Pasteur.
Leah here from LeahForSci.com, and in this video we'll introduce the concept of chirality, looking at enantiomers, stereoisomers, chiral centers, and more. You can find this entire series along with my practice quiz and cheat sheet by visiting my website, LeahForSci.com/chirality. Chirality falls under the topic of stereochemistry. Specifically, we're looking at stereoisomers. Don't forget that isomers are molecules with the same molecular formula, but something is different about them. Constitutional, rotational, conformational, different types of isomers. And the stereo portion tells you that you have the same molecular formula, same connectivity, meaning the order of atoms, but the difference is their specific orientation in space, meaning where they're locked into. Now this can include cis-trans isomers over a double bond or a ring, or stereoisomers, which I think of as chiral isomers, RNS. When I think of chirality, I think of handedness for the molecule. Many people are right-handed, some people are left-handed, and different tools and machines are meant to be operated with one hand or the other, the right or the left hand. Imagine taking one of those big, heavy, fancy gloves that's meant for your right hand and putting it onto your left hand. It just doesn't work. Right now we're looking at the top of my right and left hand, and they look about the same. I have thumbs in the same place, fingers in the same place, and when I turn it over, they still look the same. So while hands are the same though, notice that no matter how I turn them, imagine there's a mirror right here between them. Right now, my thumbs are mirrored, fingers are mirrored. There's still an imaginary mirror between them, still an imaginary mirror. No matter how I turn them, it appears that there's an imaginary mirror between them. But now what happens if I try to superimpose them? Well, my thumbs are sticking out, so if I turn it, now my fingers are in opposite direction. If I flip my hand so that my thumbs and fingers are aligned, well, my palms are in opposite direction. No matter what I do, there is no way for me to perfectly superimpose my right and left hand, making them mirror images to each other. So we agree that hands are mirror images to each other, and if these are your right and left hands, palm down on the table, they are the same, but they're mirror images of each other. And the only way that you can superimpose a hand would be if you took a thumb and added it to the other side, assuming the fingers were the same, took a thumb and added it to the other side. Now you see the right and left hand are exactly the same. In fact, there is a plane of symmetry going right down the middle, and that is the key. If there is symmetry, then your two hands will be superimposable, and they will not be unique. A right two-thumb glove will fit a left two-thumb hand, and the other way around. When thinking of chirality, we're typically looking at a chiral carbon. Every now and then you'll see a molecule that is chiral as a whole, or a nitrogen, for example, with 4 substituents and a positive charge. 99% of the time, it'll be a chiral carbon. A chiral carbon must have 4 unique substituents. If they're not unique, it's like having a two-thumb hand, and they'll be superimposable. In organic chemistry, it helps to look and hold a 3D structure. If you don't have a kit yet, get one on Amazon by going through layatforsci.com/kit, and if you purchase through my link, I do get a small commission. So notice here we have a central carbon atom with 4 unique substituents. This is considered the chiral or asymmetric center, and it's tetrahedral because it's sp3 hybridized. So notice that I have 2 apparently same looking structures where each one has a chiral center and the 4 same substituents. If you look at the 2 molecules, you can see an imaginary mirror between them because they are perfectly reflected in each other. And as I turn them, they are still perfectly reflected in each other. Since these are chiral with an sp3 central carbon and 4 unique substituents, because they have a mirror between them, they're considered enantiomers or mirror images. And no matter how I turn them, I can always find that mirror between them. But now if I try to superimpose them, let's see what happens. To place one on top of the other, I need these substituents to line up. So let's flip it and line up the red and the green. But look at what happened. The blue and white do not line up. If I try to switch it so the blue and white are lined up, then look what happened to the red and green. They don't match. Just like with my hands, something is sticking out. Remember, with thumbs or fingers, here the only way to line up 2 of the substituents is to have the 2 other substituents be opposite. In fact, the only way I can superimpose these 2 is if I take some of the bonds and physically break them, moving the substituents around, just like the example of moving a thumb to the other side. And now, look what happens. The blue is lined up, white, green, and red, they are perfectly lined up. They're still chiral, but now they're 2 of the same chiral molecules rather than mirror images of each other. Let's prove it by trying to reflect them in each other. But look at that. The green and blue are reflected, but the red and white are opposite. They don't line up. If I try to put a mirror between the red and white, now the blue and green don't line up. So no matter what I do, I will not be able to show these as mirror images, because if they're chiral and they're the same, they're not enantiomers of each other, right? They're either the same or enantiomers. Now let's see what happens if instead of 4 unique substituents, I have only 3. So we'll take off the green one and swap it for white. So let's start with creating mirror images. I have the red and blue. Red and blue. They are perfect mirror images of each other. But how is it possible to have mirror images if I can take the same molecule and superimpose it on the other one? How is a superimposable molecule also a mirror image? And the answer is 2 of the same substituents makes this molecule symmetrical. Notice there's a line of symmetry going right down the center. Again, a line of symmetry. No matter how I turn it, I can find that symmetry, and that makes this molecule achiral